Dear students, now let us consider work energy theorem for a variable force. First we have statement, but the statement is same whether the work energy theorem is for a constant force or for a variable force. The statement is same. Work done is equal to change in kinetic energy. The only thing is, how do you identify a constant force and a variable force? If force is given by some numerical value, then it is a constant force. If a force is given by, for example, 5 plus 4x, it is clearly visible that force is a function of x. That's why it is written like this. So in this way, if force is a function of some variable, then it is a variable force. This is a variable force. So whether it is a constant force or variable force, the statement is same. Work done will be equal to change in its kinetic energy. Now let us prove for the case of variable force. Proof. We know that K is defined as half m v square. Now let us differentiate this with respect to time. dk by dt is equal to d by dt of half m v square. So half m being constant or written outside, if you differentiate v square with respect to time, you get 2v, and v when differentiated gives you dv by dt. 2 gets cancelled, and here m v dv by dt means rate of change of velocity, and that is acceleration. Since a is equal to dv by dt. Now, but here m a v, by Newton's second law, f is equal to ma. F is equal to ma. Therefore, here in place of ma we can write f, and here next v. So dk by dt is equal to f into v. And also we know that velocity is rate of change of displacement. Therefore, we write dx by dt, here dk by dt. dt gets cancelled. dk is equal to f into dx. But here f is a variable force. Therefore, we must write dk is equal to, force is a function of x and dx. Like this we must write. Now integrating. Now integrating on both sides. Here we are integrating from lower limit to higher limit. Here the variable is kinetic energy. Therefore, here the lower limit is initial kinetic energy and upper limit is final kinetic energy. and here it is x position. Lower limit is initial position, upper limit is final position. When we integrate dk, we get k. And on right hand side, you must be reminded about what definition you gave to the variable, the work done by a variable force. See, previously how we defined work done by a variable force. Work done by a variable force was defined as W is equal to f of x dx xi xf. In this way we defined work done by a variable force. Now you see, we see the same thing. So this stands for work done by a variable force. So work done, or W is equal to substituting upper limit kf minus substituting lower limit ki. So work done is equal to change in kinetic energy. So in this way we have proved the work energy theorem. Now let us do one problem on this. In the solved example 6.6, a block of mass m is equal to 1 kg moving on a horizontal surface with speed vi, initial speed 2 meter per second, enters a rough patch ranging from x is equal to 0.10 meter to x is equal to 2.01 meter. The retarding force Fr on the block in this range is inversely proportional to x over this range. And how the retarding force is a function of position, that is defined here. Fr is equal to minus k by x for x value between these two numerals. Between these two numerals it is equal to minus k by x, and outside the interval it is 0, where k value also given, proportionality constant value also given. What is the final kinetic energy and final speed of the block as it crosses this patch? So this is just like previously we did a problem, bullet passing through a soft plywood. This problem is also just like that. So let us note the data and draw a diagram to easily understand the problem. Solved example 6.6. Solved example 6.6. Here mass 1 kg and velocity, initial velocity 2 meter per second. Here, so the force, see here the block is passing through a patch, and let us draw a diagram for that. X is equal to 0.10, x is equal to 2.01. From here to here, the block is being stopped by a stopping force. See the stopping force, how the stopping force is defined. The stopping force is defined as minus k by x. From 0.1 to 2.01 meter. That is from here to here. Suppose here minus infinity, here plus infinity. From here to here, the stopping force has this much value, and outside the interval for less than 0.1 and greater than 2.01 on left side of this patch and on right side of this patch it is 0. Outside the range it is 0, and here k is given where k has what value given? 0.5. So now what is asked here? Number 1. What is the final kinetic energy? Kf is asked. And what else is asked? Final speed. Vf. Vf also asked. Now we solve the problem using work energy theorem. According to work energy theorem for a variable force. Work energy theorem for a variable force. How can you say here the force is variable? The stopping force is a function of x, therefore it is a variable force. Whether it is a variable force or a constant force, its statement is same. Work done is equal to change in kinetic energy. That's all. So first let us find work done. Work done by a variable force. W is equal to work done by a variable force. W is equal to f of x dx xi to xf. In this way it is defined. Now here these are the limits, lower limit, upper limit. Now see the diagram, minus infinity to 0.10, force value 0. On x-axis you have taken x value, and on y-axis we have taken force. This is origin. This is origin. Okay. So from minus infinity to 0.10, force is 0. Into dx plus from this value to this value the force is defined by minus k by x. Minus k by x dx plus Here to here again 0. 0. Work done is equal to, here 0 and something 0 plus, here minus is there, k value given 0.5, 1 by x dx, here x is equal to 0.1, here x is equal to 2.01. This also becomes 0, this becomes 0, this becomes 0, here this is dx. But here in integration there is a formula, but 1 by x when integrated with respect to x, we get log ex. If we integrate 1 by x, we get log x to the base e. So here, what is there here? Minus 0.5, 1 by x dx, x is equal to 0.12, x is equal to 2.01. So when we differentiate this, we get log x e, here 2.01 upper limit, here 0.1 lower limit, and here minus 0.5 log e upper value 2.01 minus log e lower limit 0.1. This is w, but we know very well that log m by n is equal to log m minus log n. This is an identity in logarithms. So making use of this, we can see this is in this form, therefore this can be converted into this form. Therefore w is equal to minus 0.5 log m by n 2.01 by 0.1. So we substituting the values, we get the answer minus logarithm of this value 2.01 by 0.10 This is equal to 201 by 10 or 20.1 log 20.1. This value can be seen from tables. Substituting the value here and multiplying that by 0.5, we ultimately get the answer as minus 1.5 joules. So on LHS, work done was there and we have calculated that. Now change in kinetic energy. Now here we have chosen left hand side. Now right hand side. On right hand side, change in kinetic energy is there. That is Kf minus K. Kf value we have to find out. K, initial kinetic energy means half m vi square. Mass 1 kg, initial velocity 2 square minus 2. So substituting 2 and 3 in 1. Work done is minus 1.5 is equal to change in kinetic energy is Kf minus 2 or Kf is equal to so in this way we form an answer. Now we need find final velocity also. Making use of this value, we can find C Kf is equal to 0.5. Final kinetic energy means half m Vf square is equal to 0.5. Vf square is equal to 2 into 0.5 by m, and Vf is equal to 2 into 0.5 by mass is 1 kg and square taken that side becomes square root. So here we get 1.0 under root, that is equal to 1 meter per second. So this is another answer. That's all. Now let us derive a relation between kinetic energy and momentum. You know very well that kinetic energy is defined as half mv square. Similarly, momentum is defined as product of mass and velocity. Now we want relation between K and P. Let us take kinetic energy, that is half mv square. Multiply numerator and denominator by m. Then in the numerator you have m square v square by 2m, or mv whole square by 2m. But mv is nothing but momentum. So p square by 2m. So in this way, the relation between kinetic energy and momentum is derived. Now let us consider a short answer question. Second, a lorry and a car moving with the same momentum are brought to rest by the application of brakes, which provide equal retarding forces. Which of them will come to rest in shorter time? Which will come to rest in less distance? So first let us consider which of them will come to rest in shorter time. SCAQ short answer question. Second, in this first question is which of them in shorter time. So now by Newton's second law, F is equal to F directly proportional to delta P by delta T, or F is equal to we can write K into delta P by delta T, K value 1, therefore we can just write but K value is 1, therefore F is equal to delta P by delta T, or delta T is equal to delta P by F. In the given problem, so what is given? Let us see in the given problem. In the given problem, a lorry and a car moving with same momentum. Momentum is same, both have same momentum. See, they have started with some momentum. For example, car has some initial momentum Pi, final momentum 0 because it came to rest. Next, lorry, its initial momentum is Pi dash, final momentum 0. Okay, now here change in momentum is 0 minus Pi, minus Pi. Here change in momentum 0 minus Pi dash, minus Pi dash, 0 minus Pi. We need not write all this in this much detail. Mm, very easy here. In the problem what is given, they both start with same momentum. Both lorry and car start with same momentum. Both have same momentum. That is PA same. And after applying brakes, both come to rest. Therefore, PF also PF is 0 for both. So the change in momentum will be same. Change in momentum same. Same minus 0 same. Now coming for retarding force. In the problem it is given. Are brought to rest by the application of brakes which provide equal retarding force. Retarding force is same. Retarding force is same for both. Momentum same, retarding force same. Therefore, stopping time also will be same. For both. Therefore, stopping time also same for both. This is over. Now our second concern is what is asked in the second one, which will come to rest in less distance. The distance it travels before it stops. That is less in which case. Now, see work done. Let us use work energy theorem. By work energy theorem, work done is equal to change in kinetic energy. Work done means here force F dot D. Work done is equal to force dot D, F dot D. Work is defined like this. Change in kinetic energy means Kf minus Ki. Here Fr means retarding force. You are applying brakes. The brakes exert some retarding force. So this can be written as Fr d cos theta is equal to Kf. See, finally it is coming to rest. Therefore, final kinetic energy is 0. And here K. What about theta here? What is the angle between stopping force and displacement? Stopping force is always in opposite direction to the displacement. If the displacement is to right hand side, stopping force is in opposite direction. Always the angle between the two is 180 degrees. Therefore, cos 180 degrees is equal to minus 1. So here f for d cos 180 is equal to minus ki, its value minus 1. Therefore minus f for d is equal to, but just now we have proved it, kinetic energy is equal to p square by 2m. Kinetic energy is equal to p square by 2m. Initial kinetic energy means initial momentum. So you can write here pi square by 2m. Minus minus gets cancelled. Therefore we can write the stopping distance d is equal to pi square by 2 f for m, 2f for m. Now again, both lorry and car start with same momentum. Retarding force same for both. They both have same momentum, and on both retarding force is same. 2 is a constant. So here let us write given pi is equal to same for both. Similarly, f for, that is retarding force, same for both. Therefore d is inversely proportional. So same, this same, this same. So m is remaining. So d is inversely proportional to m. Before it comes to rest, how far it travels depends upon mass. The traveling distance is inversely proportional to its to the mass of the vehicle. If the in case of lorry, mass is more, so the distance traveled will be less. For lorry, mass is more, hence d is less. For car, mass is less, hence d is more. Now let us consider concept of potential energy. Previously we considered kinetic energy. How we defined kinetic energy? Energy possessed by a body by virtue of its motion. When a body was moving, it had kinetic energy. Now what about potential energy? When it possesses potential energy. Definition is given like this: the energy possessed by a body by virtue of its position or configuration is called potential energy. We consider potential energy of a body in two separate cases. First, position. Suppose a body is lying on floor. Here we say its potential energy is 0. If you hold the same object at some height, then we say it has some potential energy, and its potential energy is equal to mgh. As far as a body is given, its mass is constant, at that place g is constant. It means potential energy is depending upon height. On the surface of the earth, the h value is 0, that is why here its potential energy is 0. And as it is moved upper and upper, its potential energy is getting increased. So here the body possesses energy by virtue of its position. Therefore, this is its potential energy. For example, in our houses we have overhead water, water reservoir, water tank. With the help of electric motor, we pump water and store water inside the water tank. The water tank being at some height from the earth's surface, the water inside the reservoir will have some amount of potential energy. Here also, simple pendulum is executing oscillations to left and right. At this level, at the lowest point, we take potential energy is 0. As it is moving higher and higher, its potential energy increases. At the left extreme or at the right extreme position, here the P is maximum. Here also P maximum. So these are examples for potential energy acquired by way of its position. Now configuration. Let us consider this spring. This is in its normal position, neither stretched nor compressed. It is at rest. So inside this there is no potential energy. But when you apply some force and compress the spring, see, by applying force and compressing it, you are doing some work, and all the work is stored as potential energy inside the spring. Just like that, here what you are doing, you are applying force in stretching the spring. To stretch a spring also you have to do some work, and the work done is stored as potential energy inside the spring, and in this way it is possessing some potential energy, and this is by virtue of the configuration. Here also a bow, it possesses some potential energy by way of configuration. Okay, now let us derive an equation for the potential energy. Okay, before deriving the expression, let us consider this further. Here, one more example. Earth crust, it is not uniform. Earth crust is not uniform. It has several discontinuities, dislocations. So these are called as faulty lines. faulty lines. That's why sometimes earthquakes occur. And when earthquakes occur, these faulty lines readjust themselves. Uh, and when an earthquake occurs, we see kinetic energy, movement of some objects. So here, the stored energy releases in the form of kinetic energy. Here, let us see first example. Let us see here. Potential energy is the stored energy by virtue of the position or configuration of a body. See here, you are storing water on overhead water tank. There, the energy is stored by virtue of its position. And if you take here, either by compressing the spring or pulling the spring, the work done is stored inside the spring. Here, by pulling the simple pendulum to one side, to either side, it is moving up, and the work done in pulling is stored as potential energy. Here also, in the example of bow, you are pulling the arrow back side, so that here some amount of potential energy is stored inside the system. See here what he says.